Chapter 20, Heat and First Law of Thermodynamics. Before starting this chapter, I know that all of you have some idea about thermodynamics because I've already taught the students in earlier years, and they have always told me that they study thermodynamics in chemistry. So they find usually these two chapters easy, which are chapter 20 and chapter 22. So I hope they might be easy for you also. And there's a small difference when we apply physical formulas or formulas in physics, في شوية difference, but they are the same ideas and everything is the same. So let's start first to understand what is a thermodynamic process. Usually when we have some system, which the system can be a gas or it can be a liquid, mainly we will be talking about the gases, we won't talk about liquids. When we have a thermodynamic system, this thermodynamic system, because it contains atoms, these atoms are in motion. If I want to describe this system, it's described in terms of parameters that I can measure macroscopically, that I can measure, that I can see and measure. I won't talk about the kinetic energy of the particles. I won't talk about the potential energy of the particles. These are internal energies. I will talk about macroscopic parameters. These parameters are pressure, volume, mass of the system that I have, and its temperature. Mainly pressure, volume, temperature. I'm interested in these three parameters if the mass is constant. So إذا أنا عندي system, thermodynamic system, اللي هو بالنسبة إلي الغاز, okay, usually I study its pressure, volume, and temperature. These three things. هلا الماس shall be constant لأنه إحنا بناخد دايما system confined in a container or confined somewhere, so the mass is constant. So what's varying will be pressure, volume, and temperature. Once we study these parameters, I can understand what's happening for the system, if it's increasing pressure, increasing volume, decreasing volume, or decreasing temperature. So when one of these three, pressure, volume, and temperature, changes, I can say that I have a thermodynamic process. So when a system changes its state, one of pressure, PVT, one of them, okay, so I can say that I have a thermodynamic process. Usually when we will work, we will notice two types of processes: a reversible process and an irreversible process. هلا نحن بكل شغلنا ما بيهمنا irreversible process. We only care about a reversible process. What's a reversible process? A reversible process takes place when the system is always in thermal equilibrium. يعني for example أنا بدي غير البريشر للسيستم. Okay, when pressure changes أكيد وحدة يا الفوليوم يا التمبريتشر رح يتغير، بس الفكرة إنه أنا وعم غير البريشر أو عم غير الفوليوم لازم أعمل change بشكل إنه it's achieved very slowly. The change is achieved very slowly. ليه كرمال أنا أعمل نوع من الثيرمال equilibrium ما بين خطوة وخطوة. So I will give you an example. So when I'm changing volume, for example, I have to go through the process of changing the volume slowly بشكل انه بين لحظة ولحظة، انه مش دغري مثلا اذا انا عندي سيلندر وبستون اضغطها دغري بسرعة، لا، لازم امشي شوي شوي، صغر الفوليوم شوي شوي لحتى يصير عندي نوع من الثيرمال equilibrium ما بين لحظة ولحظة. هيدا بسميها reversible process. بالreversible process اوكي في عندي characteristics مهمين، انه انا بقدر احسب الورك، بقدر بحسب الانتروبي، بقدر احسب اشياء كتير. بلا لما تكون الامور irreversible it's hard to calculate them, so things go different. اوكي، وكمان بالreversible process اذا انا رايحه from one direction to another، يعني عم changing PVT to new P2 V2 T2, I can go back to P1 V1 T1. This is a reversible process. But if I'm going through an irreversible process, إذا أنا رايحة من P1 V1 T1 عند P2 V2 T2 ما فيني أرجع عند P1 V1 T1. So a reversible process is a process, as you can see, it can be achieved through thermal equilibrium. لازم أعمل عملية التغيير بشكل كتير بطيء، اوكي، لحتى بين لحظة ولحظة يكون السيستم تاعولي عم يعمل equilibrium وبرجع أنا بكفة change. Okay, so this is called a reversible process, which will be our study here. We won't study irreversible processes. We will only study reversible ones, because reversible processes allow us to calculate work, heat, etc. in terms of integrals. Okay. هلا, if I've started from a certain thermodynamic state with P1, V1, T1, and then I change pressure, volume, and temperature and get back to the same P, V, and T, this is called a cycle. It's called a cyclic process. When I change my parameters and then get back to the same parameters, this is a cycle. I hope you all know this information. Okay, so بالنسبة للreversible processes, there are 4 important reversible processes. We will see them during our course, which are the isothermal process, the adiabatic process, the isobaric process, and the isochoric process, or also called isovolumetric process. Okay, what's an isothermal process? Let's start with the first one. When I try to change the properties of the system that I have at constant temperature, then the process is called isothermal. Okay? The adiabatic process is the process when I try to change the properties of my gas, which are P, V, and T, but without the flow of heat into or from the system. Q is 0. يعني بالadiabatic السيستم تاعه اللي هو الغاز ما بياخد ولا بيعطي heat. اوكي, الهيت تاعته 0 او الكيو تاعته 0. الهيت flow in او out is 0. الايزوثيرمال بس كون انا عم غير البي والتي, الفي والبي, بتكون التمبريتشر كونستانت. اوكي, بالايزوباريك بروسيس بالايزوباريك بروسيس بهيدي الحاله البريشر is constant, so I vary volume and temperature. When they both vary, the pressure is constant at this instant. Okay, you know that we have 3 things: pressure, volume, temperature, so they will vary, the 3 of them. إذا واحدة منهم ثابتة بيبقوا الاثنين بس بيتحركوا. بالايزوكوريك بهيدي الحالة بكون عم بعمل change للكاركتر أو للproperties of the system, but at a constant volume, so I will be changing pressure and temperature, and volume at this instant will be constant. Okay, so for example إذا أنا عندي غاز محطوط بجار ومسكر أو بكونتينر ومسكر وأنا عم حميه، إذا أنا عم حميه يعني أنا عم علي التمبريتشر, so what will change؟ رح يتغير البريشر تاعيته بينما الفوليوم رح يبقى ثابت. Assume it's closed in a container and the container has a constant volume. So this is for the isothermal, adiabatic, isobaric, isochoric. So نحن عم نحل, we have to take into account the type of the process, because it determines the way of calculating the work done by the gas and the heat taken or absorbed or exhaled by the gas. These processes are very important because they tell us how to calculate or how to find the unknowns that we will be searching for or we will be interested in. So before entering to talking about these processes, let's remind you with an ideal gas. We will be interested in studying only ideal gases, nothing else than ideal gases. For an ideal gas, the equation of state is PV equals an RT. You all know this formula. So P is the pressure. It must be in Pascal. Okay, it's in Pascal, Newton per meter square. It's never in atmosphere, for example. But when in atmosphere, I have to change in Pascal. V is the volume in meter cube. N is the number of moles of the gas. Okay, R is a constant. It's equal to 8.314. Usually this constant is given in exam. And T is the absolute temperature in degree Kelvin. When I say absolute temperature, I mean in degree Kelvin. So you all know how to, I've added 2 notes down the slide, that the relation between the Kelvin degree and the Celsius degree. So you can see that T temperature in degrees Kelvin is equal to the temperature in degrees Celsius plus 273. This is for the temperature, and n, you all know if n is not given in the exercise, for example, you can calculate n by dividing m over m, where m, small m, is the mass in grams, m is the mass in grams of the sample I'm studying, and big M is the molar mass of the sample, so mass over molar mass, mass in gram, molar mass in grams, so you will get the number of moles. I think this information you must know them from chemistry. So this is for an ideal gas. This equation is very important. We will use it everywhere. Okay, you can see from this equation we are relating if n is constant, and if I'm taking a gas that's confined in some container, يعني n is not changing، يعني ما عم هرب أنا غاز من مطرحها، so everything is confined somewhere. So بيبقى عندي relation between PVT. So NR is constant. So أنا إذا معي two of them I can find the third. يعني إذا أنا معي PV فيني لاقي T، إذا معي VT فيني لاقي P، إذا معي if I have two of them I can find the third. So you can see that the three of them are related in some way, PV equals nRT. If I know two, I can find the third. Okay, so this is the benefit of an ideal gas. We will use it when we derive several equations, so let's keep it in mind. First, what I will explain is the work done by the force exerted by gas. This is very important to understand the work done by gas, because in chapter 22, which is the last chapter, we will be interested by the work done by the gas. So let's consider, as you can see here, a gas. We have a gas, trapped gas inside a cylinder. I have a piston. You can see this piston can move. Okay, so I have a piston. This piston has an area A. In the lecture that I have expanded the piston, so the piston moves to the left by a distance dx, and the piston has an area A, and I've said reversibly, when the piston moves a distance dx, then here the gas inside has done some work, which is the work done by the gas. For sure the gas is doing a force here, force on the piston, so the work done by the gas, it's equal to dW, it's equal to F dot dx, it's equal to F dot dx, okay, because F and dx have the same sign, so F dx, this is dx. So it's F dot dx, the force times dx. What is the F? It's the force exerted by the gas on the piston, because what's doing the work in reality is the gas, because I'm searching, remember, I'm searching for the work done by the gas. It's the work done by the gas. كلنا بنعرف إنه الforce exerted by the gas it's equal to P times A, pressure times area, because pressure for the gas is equal to F over A. So F is equal to P times A times dx, and as I have already said that A times dx is equal to dV, so we will get dW equals P dV. What is dV? dV is the change in the volume of the system. Okay, so work done by the gas, or infinitesimal work done by the gas, dW, it's equal to the pressure of the gas times dV, which is the change in the volume of the gas. This is the work done by the gas. Let me erase all this. Okay, so this is work done by gas, work done by gas. This is the pressure of gas, and this is change in volume of gas. This formula, the dW equals P dV, is true for any reversible process. Any reversible process, I can apply this formula to find the change in the work done by a gas. So if I'm expanding from a point 1 to point 2, point 1 has the characteristics P1, T1, V1, to point 2 with the characteristics P2, V2, T2, I simply have to integrate integral P dV. Okay, so this is, remember, this is the work done by gas. Work done by gas. This is very important. You all know that always pressure is positive, so dV can be positive or negative. dV هي change in volume، يعني هي إذا بدكم هي مثل دلتا V بس على مقاس أصغر. Okay, so dV is change in volume. if dV is positive يعني إذا الفوليوم عم يكبر I have expansion. So in the case of expansion لما يكون أنا عم يكبر الفوليوم للسيستم تعولي دايما the work is done by the gas. Okay, the work done by the gas is positive. W is positive. In the case of compression لما يكون عندي dV negative إذا الفوليوم عم يصغر إذا الفوليوم is decreasing so dV is negative بهيدي الحالة الورك بيطلع معي negative. شو يعني work done by gas negative؟ يعني مش هو الغاز اللي عم يعمل الورك يعني الانفايرومنت عم يعمل work على الغاز. اوكي so if the work is positive هيدا بيعني انه الغاز هو اللي عم يعمل الورك وعم يدفش البستون لبرا. طيب اذا البستون عم تفوت لجوا يعني الفوليوم عم يصغر وطلع معي الورك نيجاتيف هيدا شو بيعني؟ بيعني انه الانفايرومنت او الاكسترنال سيستم هو عم يعمل فورس على الغاز او عم يعمل ورك على الغاز. سو كرمال هيك اذا انا بحسب الورك للغاز بيطلع نيجاتيف because مش الغاز اللي عم يعمل ورك هو عم ينعمل عليه ورك للغاز. So this is the meaning of W positive or W negative. If the gas itself is doing work, if it's moving the piston, so W will be positive. If the gas is receiving the work, W will be negative. Most of the problems will contain a graph, a PV graph. This is a PV graph which draws the process in a relation between P and V. You can see that the vertical axis is pressure and the horizontal axis is volume. This is called a PV graph. So this is a process. You can see this is a process. It starts from 1. Here, I'm talking here. So it starts from 1 and then goes to 2. You can see that this process starts from here to here. So دايما إذا أنا بدي أحسب الورك it's equal to integral من محل ما بلشت لحد ما خلصت 1 to 2 PdV. Okay, so if I have the equation of this line, which is this line, I don't know here the type of the process, but if I have the equation of this line, because this is P in terms of V, so أكيد ال P بدها تساوي شيء in terms of V. So if I have the equation of this line, I can insert it and find the integral, or simply integral PdV is equal to the area under the curve. The area under the curve. Okay, so you can see that here أول شي هون from 1 to 2 هيدي اللي هون هيدي عبارة عن expansion. كيف عرفت أنا expansion؟ لأنه from 1 to 2 السهم رايح على اليمين الvolume is increasing سهم على اليمين. I will erase it so that you can see the arrow. سهم رايح على اليمين الvolume is increasing. لما يكون الvolume is increasing يعني أنا عندي expansion. اوكي اذا انا بقدر احذر الاريا او الاريا هي كلير اوكي الورك دايما بما انه قاعده الورك هي انتجرال بي دي في سو انتجرال بي دي في مثل الماث انتجرال اف اوف اكس دي اكس ما الاف اوف اكس عندي انا هون البي والاكس هي الفي so it's the same integral p dv. This will give me the area under the curve. So الورك in reality is the area under curve. هلا in the second figure هي figure B هون أنا عندي from 1 to 2 لاحظوا the arrow is going to the left. So I'm going from large values of V to small values of V. This is a compression. Okay, this is a compression. This is an expansion. Remember, this is an expansion. كيف عرفت؟ From the shape of the arrow. If I'm going to higher values of V, it's an expansion. If I'm going to lower values of V, it's a compression. بهيدي الحالة هون الwork it's equal to integral P dV مثل العادة. It's equal to minus the area under the curve. Under minus هو حاطين هون area بس minus the area under the curve. Under curve. ليش minus الاريا؟ لأنه أنا من شوي شرحت إنه بحالة الإكسبانجن الwork must be positive. بحالة الكمبريشن الwork must be negative. So it's not enough to write the area. It's minus the area under the curve. Okay. دايما لما تحسب الwork ببلش من محل ما بلشت من ال1 لعند ال2. Note that the integral is from 1 to 2. From 1 to 2 دايما من محل ما ببلش لمحل ما بخلص. هو لحاله بيطلع الانسر. أنا I just integrate integral from 1 to 2 من محل ما بلشت لحد ما خلصت PDV. okay, بس it's good to know that this integral PDV what does it have a meaning in terms of the graph. It means that it is the area under the graph. طيب اليمين إذا أنا رايح من ال1 لل2 من ال2 لل1 الاريا no, they must be related by a minus sign. لأنه إذا أنا رايحة from small values to big values of volume, I'm expanding, so work must be positive, so it's the area. If I'm going from large values to small values of V, so I'm compressing, in this case work must be negative, work done by the gas. I'm saying work done by the gas, okay? So work in this case it's equal to minus the area. كمان في شغلة صغيرة كمان أكيد بالماث أخدتوها I guess. أنتوا لما كنتوا بدكم تجيبوا إذا عندكم function f of x بدكم تجيبوا area under this function, so you always say this is x1, this is x2. You say that the area is equal to integral x1 لل x2 f of x dx. ولا مرة كنت تحطوا x2 x1 بتبلشوا من الصغير لعند الكبير. اوكي سو كرمال هيك هون الورك بيساوي الاريا، بينما بالجراف A الورك بيساوي الاريا، بينما بالجراف B الورك بيساوي ماينس الاريا، لانه سيمبلي انا عم بعمل الانتجرال V1 ل V2 والV1 اكبر من الV2، يعني انا عم بعمل انتجرال بالقلب، يعني انا بلشت من الكبيره ورجعت جيت لعند الصغيره، so it must be minus the area. Okay, this is as a mathematical proof for what I'm saying. So the work done by force exerted by a gas during a thermodynamic process is equal to the area under the curve in a PV diagram. So this is what I have already said. Now let's study the different cases for different processes and how to find the work done by the gas. Let's start first with an isobaric process. For an isobaric process, the pressure is constant. So simply the integral will become W integral from 1 to 2 P dV. تطلع ال P لبرا، ال P constant. I will get P dV. So integral لل dV هي V. I will substitute V2 minus V1, which is equal to PV. So it's simply P delta V. Okay, V2 minus V1. This is in the case of an isobaric process. هلا إذا أحيانا نعطيني temperature, I can relate it to temperature like P delta V equals NR delta T. Why? I will explain why. Because PV2 minus PV1 it's equal. Using the ideal gas theorem, PV2 it's equal to nRT2. PV1 يعني هي البريشر على ما هي البريشر is constant. PV1 it's equal to nRT1. So I will get nRT2 minus T1. So it's either P delta V or nR delta T. Both of them are correct. Now if I have an isochoric process where V is equal to constant, then dV here it's equal to 0. Once dV is equal to 0, the integral is equal to 0. Okay? So in the case of an isochoric process, the work is 0. No work is done. There must be a change in volume. If I have an isothermal process, in the case of an isothermal process, the temperature is constant. Temperature is constant, so I will try to integrate the work from 1 to 2 P dV. I will replace P by its value from the ideal gas equation. So أنا بعرف إنه ال PV equals nRT. هيدا بيعطيني إنه ال P it's equal to nRT over V. حطيت ال P بقيمتها. هلا انا معي temperature constant, so temperature nRT بتطلع لبرا، بيبقى معي جوات الانتجرال dV على V. ليش عملت هالتريك كلها؟ لانه انا معي اثنين variables، ال P variable وال V variable. اوكي، بينما ال T هي constant، فحاولت اكتب ال P in terms of V كرمال يبقى معي one variable اللي هو ال V. ما في مشكله فيني اكتب in terms of P، يعني حول اثنين ل P، but it will take longer time to integrate, so this one is easier. بصير بدي اعمل ال dV. This one is easier. So I will get nRT, nR اللي بتظهر لبرا، nRT بتطلع لبرا الانتجرال because it's constant. So I will get dV over V. For sure it's equal to ln V2 over V1. It's clear here that if V2 أكبر من V1 then V2 على V1 is greater than 1. وإذا الريشيو أكبر من 1 هيدا بيعني إنه ln بيطلع معي positive. So the work will be positive. So هيدا ln V2 على V1 is positive, so I will get positive work لأنه عم يصير في عندي expansion. إذا ال V2 أصغر من V1 يعني اللين رح يطلع معي نيجاتيف، يعني الورك معي نيجاتيف لأنه أنا عندي بيكون compression، ولست يكون في عندي compression بيكون الورك done by the gas is negative. يعني هيدا إنه بيعني إنه مش هو اللي عم يعمل الغاز، مش عم يكبر الفوليوم الغاز، بالعكس في حدا عم يضغطه من برا وعم يصغر له الفوليوم. Okay, so this is the work done by different processes, which are the processes that we are going to consider later. Now let's talk about the internal energy. نحن حكينا عن macroscopic parameters of our system, which are P, V, and T, but we have to understand the energy of the system, and mainly the internal energy. The internal energy, because our system is composed of particles, these particles are in motion, they collide together, they repel each other, they have interactions between each other, so there's some type of internal energy. Any isolated system, such as a gas in a cylinder, has an internal energy. We give this internal energy the symbol U, which is the sum of internal kinetic energy, because all the particles inside our system are in motion. They translate, they rotate, they vibrate, they are molecules, they move. They move everywhere, they have a kinetic energy. Because I'm looking inside my system, this is called an internal kinetic energy. In addition to this internal kinetic energy, we have an internal potential energy, because these particles also collide, repel each other. They have different interactions between each other. This internal energy, for sure, can be measured in terms of the parameters of the gas, which are the pressure, volume, and temperature. So U is a function of P, V, and T. Okay, because it's an energy, and I usually don't measure internal kinetic energy. I don't measure internal potential energy. I can measure pressure, volume, and temperature. So I will say that this internal energy is a function of these three parameters. Experiments have shown that this internal energy for an ideal gas is only a function of temperature. It only depends on temperature. It does not depend on anything else. Yani, for example, if two gases have the same different pressures, different volumes, same temperature, they have the same internal energy. Okay, so we have seen that in experiments. U depends only on temperature for an ideal gas. This is true for an ideal gas. Okay, so two gases of same, for sure, for same number of mole, same characteristics, same type of gas, I mean, if they have different pressures and volume, same temperature, they must have the same internal energy. If we are considering a cycle, yani if we are changing the system, the parameters of the system, starting from P1, V1, T1, and then going back to the same parameters P1, V1, T1, and we are doing a cycle, once we get back to the same temperature, we get back to the same internal energy. So we say that delta U, which is the variation of the internal energy of my system, is equal to 0 for any cycle. لأنه أنا لما بلشت بحالة ورجعت برمت ورجعت على نفس الحالة اللي أنا بلشت فيها، رجعت على نفس ال P، نفس ال V، نفس ال T. وأنا من شوي حكيت إنه same temperature يعني same internal energy. يعني بس أرجع أنا على نفس الحالة اللي بلشت فيها، هيدا بيعني إنه my temperature did not change. يعني initial final same temperature, so delta U is equal to 0. So delta U is equal to 0 for any reversible cycle. This is true for any reversible cycle. We can use this formula when needed, when we solve. So if the cycle consists of reversible processes, it is possible that no observable change is produced after cycle is completed, and then delta U is equal to 0 for any reversible process. As I have said, when we get back to the same temperature, من بعد ما عملنا لفة ورجعنا على نفس temperature, so delta U, the change in internal energy, will be equal to 0 because U depends only on temperature, and once I get back to the same temperature, delta U will be 0. Now let's come to the first law of thermodynamics. Let's consider a system at initial state 1. So it has a pressure P1, volume V1, and temperature T1. Assume that it absorbs a quantity of heat Q. It's taking Q, and an external agent done some work on it. So W external, this is W external is the work done by an external system. It's not the work done by gas. This is something, some work done by something external. So I have a system, I give it heat, I give it work, or I do work on it. Then the system will change in state. It will be in a new P2, V2, and T2. What does the principle of conservation of energy says? The principle of conservation of energy says that the variation of the internal energy قد ايه بتتغير الانرجي تاعتها بيساوي الاشياء اللي انا اعطيته اياه. انا اعطيته هيت واعطيته work او عملت عليه work، so راح يتغير الانرجي اللي كسبها هي قد ما انا اعطيته. That's it. So delta U, the variation of delta U, the variation of internal energy، قد ايه ربح internal energy قد ما انا اعطيته heat زائد work عملت عليه. لانه لوين راحوا هدول الورك والهيت؟ ما راحوا لمطرح. They changed to internal energy. So this is the first law of thermodynamics, which is delta U equals Q plus W external. Q هي الهيت اللي أنا أعطيته إياه، وال W external is the work done by external agent, by something external, مش done by the gas, different from the work done by the gas. Okay, so كلكم تعرفوا إنه if Q is positive, then the system absorbs heat. If Q is negative, then the system produces heat and it's losing heat. If W external is positive, يعني الagent اللي برا عم يعمل work على السيستم. If W external is negative، يعني الغاز هو اللي عم يعمل work فعليا، مش إنه external agent عم يعمل work على الغاز. So this is يعني don't worry if you have negative values for Q and for W. It's completely true and it's completely logical. It has a physical meaning, which means that the exchange of energy is from one side to the other or the opposite of it. So the change in internal energy of a system is equal to the heat absorbed by the system plus the external work done on the system. Work done on the system. This is the first law of thermodynamics. هرجع عيد الكيو هي الهيت تاعت السيستم اللي عم تفوت او عم تظهر من السيستم. الورك external هي الورك done on the system، مش الورك done by the gas. work done on the gas. okay, work external work done on the gas، يعني اللي عم تنعمل على الغاز مش اللي الغاز عم يعملها. Anyway, there's something very important, that the work done by an external agent on the system is equal to the negative work done by the system on the surrounding. هلا I can see things through a different this is a piston, this is a gas, this is a gas, and it's confined inside a piston. I can see things in two different ways. فيني أقول إذا الغاز عم يعمل expansion، so غاز هو عم يعمل work، يعني عم ينعمل work على external. okay، يعني الwork تاعه للغاز بيساوي minus الwork على external. so work done by the gas is equal to minus work done on the gas. okay, it's logical. بيرجع إذا أنا عندي compression، يعني الاكسترنال هو اللي عم يعمل work, so work done on the gas is equal to minus work done by the gas. so okay, it's logical. دايما the work done, this is the work done on the gas is equal to minus work done by gas. امتى الwork done by gas positive؟ لا بعد شوي شرحتهم. الwork done by gas positive لما يكون عندي expansion، والwork done by gas is negative لما يكون عندي compression. اوكي، سو كل مرة بكون أنا عم بعمل expansion بتكون الwork للغاز positive، بتكون الwork done on the gas negative. This is done by the gas, it's done on the gas. يعني external work negative. إذا أنا عندي الwork negative، الwork done by the gas negative، هيدا بيعني انه الاكسترنال هو اللي عم يعمل work مش الغاز هو اللي عم يعمل work. I hope it's clear. إذا ما كانت clear when I allow you to speak you may ask. Okay, so we can replace W external by minus W, so we will get the first law of thermodynamics which is delta U equals Q minus W، وهي ال W هي الانتجرال ل P dV. اوكي، هلا في حدا يقول لي انه نحن بالكيمستري اخذناها دلتا يو ايكوالز كيو بلس دبليو. بقول لك ايه، انتم كنتوا تحطوا بلس دبليو بس كنتوا تعوضوا دبليو ماينس بي دي في، ماينس انتجرال بي دي في. ليه؟ لانه الدبليو بالكيمستري انتم بتاخذوها هي الدبليو هي الورك دان اون ذا جاز مش ورك دان باي ذا جاز. اوكي، سو نحن بالفيزيكس معودين نستعمل هالفورمولا لانه بتفيدنا بالشابتر 22 اللي هي الدلتا يو equals Q minus W. هيدي ال W اللي عم تشوفوها انتو اللي هي مش مكتوب تحتها external، هي work done by the gas and its formula is integral PDV، مش minus integral PDV، هي integral PDV. Okay, so I can write the first law of thermodynamics this way, or I can replace dW by du, dq by q by dq, and W by dW. This is the infinitesimal form. يعني إذا أنا صار عندي small change in energy, so a small variation of internal energy is equal to small exchange of heat minus the small work done by the gas, which is equal to du equals dq minus p dv. Okay, so this is for the first law of thermodynamics. Please, when you use this law of thermodynamics, use the method, our method. Don't use the method in chemistry, because even in survey book they have used in this chapter بهيدا الكتاب استعملوا هن بالدرس 22 بيستعملوا delta U equals Q plus W external، بيستعملوا هيدي الفورمولا. بيرجعوا بالشابتر 22 بيستعملوا الفورمولا اللي هي delta U equals Q minus W. يعني they used both formulas in this book. So هيدي الفورمولا اللي احنا بحاجتها يعني بدنا نستعملها، مضطرين نستعملها، فليتس خلاص بس ما بنستعمل غيرها. Don't use any other formula, only this one which is delta U equals Q minus W, and this W is the work done by the gas اللي أنا شرحتها بالسلايدز اللي قبل، بحالة الايزوباريك، بحالة الايزوثيرمال، وبحالة الايزوكوريك. اوكي، وهي in general هي integral P dV، هي الفورمولا اللي أنا شرحتها من شوي. Okay, let's talk now about heat capacities of an ideal gas. What's a heat capacity? Heat capacity is a constant for some type of gas. It gives me an idea about the change in energy or the energy needed or the amount of heat needed to raise the temperature of my sample by 1 degree. So the molar specific heat, this is the molar specific heat. أول شيء this is molar specific heat لأنه I have divided by n, so this is per mole. يعني أنا عم جيب للمول الوحدة من الغاز تاعولي، اسمها molar specific heat. So molar specific heat هي الهيت capacity per mole. أنا عم جيب dq على dt للمول الواحد. Okay. It is the amount of energy needed to raise the temperature of a sample of 1 mole by 1 degrees. So إذا أنا بحسب C بعمل equals 1 over n small variation of Q على small variation of temperature، وبقسم على number of moles للغاز اللي أنا عملت عليه الإكسبيرمنت، بيطلع معي constant. It's constant for the same gas، يعني كل نفس هيدا الغاز عنده نفس الكونستانت C. قد ايه أنا بحاجة لكيو حتى أرفع، بيطلع معي أنا قد ايه أنا بحاجة لهيت حتى أرفع أو change the temperature of my system by 1 degree. Okay, so this is C. يعني هيدا هو الكونستانت اللي بيطلع معي، هو عبارة عن قد ايه أنا energy بحاجة حتى أرفع 1 mole 1 degree. This is the heat capacity. هلا for sure this heat capacity depends on the method on the process I'm using for the system. If I'm moving through an isochoric process, C will be different from when I'm moving through an isobaric process, for example. So there are usually two common molar specific heats. We indicate them by using a small index. When you are going through a constant volume process, we call CV, which is the heat, which is the it's the amount of energy needed to rise the temperature of one sample at constant volume by 1 degree. بينما ال CP هي عبارة عن the quantity of heat needed to rise the temperature of a sample of 1 mole by 1 degree at constant pressure. Okay, so it depends on the process that I'm going through. Usually CVs and CP for a certain gas or for a certain type of gas is constant, and it can be found by experiments, and in certain in problems usually it's either given or we have to calculate it, and it's constant for the gas during the whole process or the whole let's say the whole example. Okay, this is for the heat capacity. Now let's talk about the variation of the internal energy. Let's make benefit of this heat capacity formula, which is C equals 1 over N dQ على dt, and try to find the variation of the internal energy. Consider a gas of N moles undergoing an isochoric process. From the first law of thermodynamics is du, small change in internal energy, equals dq, which is a small change in heat, minus pdv. Okay, which is pdv is the work done by the gas, not on the gas, by the gas. So I will substitute I'm going through an isochoric process. I will substitute the dv by 0, so I will get du equals dq. why I'm moving through an isochoric process I will tell you بس شوي بس لا أخلص الديريفيشن. So du it's equal to dq. dq is أنا ماشي بisochoric process. هلا أنا قلت cv equals 1 على n dq over dt. So cv, as you can see, أو dq it's equal to ncv dt. Okay, إذا أنا ماشي بisochoric process, so dq is أنا ماشي بisochoric process equals ncv dt. So this is dq. بيطلع مع du equals ncv dt. هيدا بيعني انه اذا انا مشيت من temperature 1 to temperature 2, then delta u, which is u2 minus u1, it's equal to ncv t2 minus t1. This is the change of internal energy. Okay, هلا هيدا change of internal energy اذا انا مشيت isochoric process from temperature 1 to temperature 2. بس نحن من شوي برهنا انه الانترنال انرجي ما بهمها البروسيس اللي انا مشيت فيها، بس بهمها الانيشال فاينل temperature. بهمها it only depends on temperature. So اذا انا انطلقت من temperature T1 وخلصت بtemperature T2, okay, then delta U it's equal to NCV delta T. شو ما كان نوع البروسيس، كانت isochoric isobaric شو ما كان نوع البروسيس، انطلقت ب T1 خلصت ب T2، اوكي، لازم تكون دلتا يو بتساوي ان سي في دلتا تي، لانه انا هلا بعدني مبرهنه انه دلتا يو ما بتعتمد الا بس على التمبرتشر. انت انطلقت بتي 1 خلصت بتي 2، then دلتا يو بتساوي ان سي في دلتا تي. اوكي، وما بيهمني انت كيف مشيت الطريق اللي مشيت فيه. So this formula delta U equals NCV delta T is true for any process because U was found to depend on temperature only. صح أنا هون برهنت على الايزوكوريك process، بس أنا already كنت برهن إنه U depends only on T. Okay, so this formula is true for any other process. Okay. Now let's come and make benefit of what we have to prove Mayer's law. Consider an ideal gas heated at constant pressure. So now we are going to heat our gas at constant pressure. So P is constant. The first law of thermodynamics, infinitesimal form of first law, takes the form du equals dq minus pdv. Okay. PdV is equal to an RT. Remember that PV is equal to an RT. إذا أنا بدي أعمل derivative يعني dPV equals d an RT. So P is constant. ال P بتطلع برات الانتجرال يبقى معي P dV equals nR dt. So I will get nR dt. Okay, so I will change du with I will flip du and dq, so I will get dq equals du plus nr dt. بدلت ال du مع ال dq. هلا رح بدل ال dq بقيمتها. انا بعرف انه at constant pressure ال q او ال cp equals 1 على n dq على dt. So ال q او dq at constant pressure بتساوي ncp delta t. هيدي at constant pressure. At constant volume ال dq بتساوي ncv delta t. At constant pressure ال dq بتساوي ncp delta t. هلا انا فيني كم بدلهم، بس انا عوضت محل السي بي. So cp equals 1 over n dq over dt. عوضت محل ال dq على dt. اوكي، قسمت هون على dt. So I've divided by dt here. بيطلع معي du على dt plus nr. I've expanded the bracket 1 over n du over dt plus r. هلا هيدي du على dt. du هي بكل الحالات شو ما كان نوع البروسيس هي ncv dt. شو ما كان، شو تكون قلت لكم انا شو ما كان نوع البروسيس هي على طول ncv dt، ما خاصه بالبروسيس. صح انا عملت لها derivation باستعمال الكونستانت فوليوم، بس هي it's the same for all types of processes. Sorry, at constant volume, but here it's true for all processes because it does not depend on the type of process, it only depends on the initial and final temperatures. So I've replaced du by ncv dt. أكيد dt مع dt بيطيروا، n مع n بتطير، يبقى معي cp equals cv plus r. So this is the formula that we are searching for, which is Mayer's law. R is the constant, which is the constant of the ideal gas, which is 8.314. Cv is a constant for it gives me the quantity of heat at constant volume. This gives me the quantity of heat absorbed by the system at constant pressure. So this is the Mayer's law. For sure, derivation is not required. It's I prefer you understand the derivation, but you are not responsible for memorizing it. For sure, it's enough to understand the formula and use it. يلا شوي وبوقف. I will hydrothermal process. Okay, I will explain the atomicity and then I will leave the rest till the next time. Let's talk about the atomicity constant. This atomicity constant appears when we are going to work. We will face this constant. It's called gamma. Okay, let's define it. Atomicity constant gamma, it's equal to cp over cv. We were going to divide cp over cv, and instead of talking about cp and cv we're going to talk about gamma, which is a constant. هلا cp أنا معي إنه هي عبارة عن cv plus r. Okay, so it's sure that gamma is greater than 1. على طول gamma أكبر من 1. هلا بما إنه الcv والcp هن characteristics للغاز اللي أنا معيه، يعني أنا إذا معي الcv فيني أحذر الcp، واذا معي السي بي فيني احذر الجاما. سو الجاما والسي بي والسي في هن كاركترستكس للسيستم، واذا انا معي وحده فيني اجيب الاثنين البقايا. يعني اذا انا معي الجاما فيني اجيب السي بي والسي في، اذا معي السي في فيني اجيب السي بي والجاما، اذا معي السي بي فيني اجيب السي في والجاما، اذا معي وحده منهم فيني اجيب البقايا الثلاثه. اوكي، سو بس بالايكويشنز usually there appears a division between Cp and Cv, so they define this constant which is called the adiabatic atomicity constant. You will see it later in later derivations. So they have found that this gamma, which is the adiabatic constant, it's equal to L plus 2 over L, where L is the number of degrees of freedom of the molecules. Okay, so they have shown that we are not responsible for this part of the course. يعني منين جابوها وكيف عملوها والى اخره. we're not responsible. I will just give you a hint كيف عملوها. So الجاما لقوها بتساوي L plus 2 over L. L is the number of degrees of freedom of the molecules. كيف يعني؟ شو يعني number of degrees of freedom؟ إذا أنا عندي ideal monoatomic gas مؤلف من أتوم واحد اللي هي الصورة الفوق. هيدا المونو اتوم، اذا عندي الغاز مؤلف من اتوم وحده، بيقدر هيدا الغاز عنده 3 degrees of freedom، يعني في يتحرك بالاكس اكسس وبالواي اكسس وبالزد اكسس، عنده 3 degrees of freedom. so ال عنده 3. اذا انا بعوض ال 3 so L equals 3 بيطلع أنا عندي gamma equals 5 over 3 so gamma equals 1.66. so رح تلاحظوا أنتم بأغلب الأسئلة اللي فيها mono atomic gas gamma equals 5 over 3. ليه؟ لأنه هي عبارة عن 5 over 3 لأن هي عبارة عن L plus 2 over L وأنا عندي 3 degrees of freedom. المونو atomic غاز بحق له يتحرك، يعني إذا أنا عندي طابة فيها تحرك بالإكس وبالواي وبالزد أوكي بثلاث اتجاهات 3 degrees of freedom. إذا أنا عندي داي atomic gas، عندي اتوم مؤلف من داي اتوميك جاز so this is a diatomic gas اللي هي الفيجر الثانيه. اوكي طيب بالنسبه للداي اتوميك جاز انا عندي two atoms attached to each other. التو atoms فيهم يتحركوا باتجاه الاكس وباتجاه الواي وباتجاه الزد واضف الى ذلك فيهم يبرموا حول بعض بالهوريزونتال بلين وفيهم يبرموا حول بعض بالفيرتيكال بلين، يعني فعليا حركتهم عندها 5 degrees of freedom. okay so we will get gamma equals 7 over 5 is equal to 1.4. كمان you will see that in most problems where we have a diatomic gas gamma will be given 1.4. you can't use it unless it's given in the problem or unless يعني نحن ما فينا نستعملها انه اذا حتى لو قال لي بالسؤال نحن باسئلتنا اذا قال لي انه we have a monoatomic gas or a diatomic gas ما فينا نستعمل الجاما، يعني ما تاخذوها constant. he might ask to find it بس انا عم لكم كيف بتعرفوها بدون ما تعملوا حسابات طويله عريضه او اذا كنتم محتارين وما عارفين اذا جوابكم صح. For a monoatomic gas it's 1.66 approximately and for a diatomic gas it's approximately 1.4. هلا this note هيدي اذا انا معطيني هو بالحقيقه الجاما وانا مضطره احسب السي في والسي بي، اذا انا بدي احسب الكيو فور اكزامبل اللي هي ان سي في دلتا تي او بدي احسب السي بي او بدي احسب الكيو اللي هي ان سي بي دلتا تي حسب وضع السؤال. سو انا محتاجه للسي بي والسي في وبس انا ما معطيني هو الا الجاما بالسؤال. so how to calculate them using gamma? what shall I do? I will substitute CP for CV plus R. So I will get CV على CV will give me 1 بيرجع plus R على CV. I will take 1 to the other side here. So I will get gamma minus 1 equals R over CV. Invert I will get CV equals R over gamma minus 1. هيدا بيعني كل مرة مع الجاما فينا احذر السي في بهالطريقة. You can memorize this formula. Okay. Memorize it better. يعني ما تعملوا derivation عم تشتغلوا. So CV equals R over gamma minus 1. هلا أنا معي إنه الجاما equals أو CP equals gamma CV. So multiply by gamma, you will get CP. So once you have gamma, you can calculate CV and CP. Okay, during this way. I will end this session till here. So I will keep the rest of the explanation till the next time because I know it's a little large, but the next one is not as large as this one. This is a little bit long, so I will leave it till next time.